Hello, and welcome. Good evening, good morning, good afternoon, good nap time, and good evening time, and good, hopefully, peaceful, relaxing night time to everybody. Thank you so much for joining. If you're going to be joining, thank you so much for watching this as a video upload later on. If that's what you're going to be doing, and indeed, I want to say welcome, welcome, welcome. Thank you so much for being here. And I'm very thankful and very grateful to see everybody old and new. Hope to meet many new friends today, as well as many returning friends if they are still up. It's a little bit late. I did have a bit of an upset stomach this evening, which came about in an unprecedented manner. Indeed, I was at the gym and I couldn't even finish my usual workout, and I had to come back after I lifted some weights, and I did not do my swimming, which made me very sad indeed, because I had to rush back with unprecedented urgency. And yes, so yeah, I think it's because I ate too many Hajmola digestive goalies. They were gonna expire, so I ate a bunch after my dinner tonight, and after that, it's just been quite a ride. You know what I mean? Like, yeah, it's been I don't know what I'm doing exactly, but it's been. Thank you so much for liking the live. Thank you so much. Who are you? Thank you for being here. Thank you for being here. Thank you for the hearts. Thank you so much for the emojis. Thank you so much for being here. Thank you for liking the live. I hope and wish and pray that we get 20 likes as usual, at least, and some money, maybe even. That would be great. But yes, so there were some Hajmola goalies in my in my kitchen cabinet. These are digestive little pills that you can have, that you're supposed to eat one or two after a meal, but they are expired currently, and so I ate too many of them to just be done and throw out the trash. And I was going to take the trash out on the way to the gym anyway, before I get to the gym. Indeed, in an unprecedented manner, my Fear says, how are you? Mexi Ghost Hunter, hello. Hi, Mexi Ghost Hunter 86. Hello, darling. Thank you so much for the emojis. Fear, hello. How are you? Says Fear. That's exactly what I'm talking about now, Fear. It is the unprecedented events of this evening, which led to many a toilet visit, because my stomach is currently upset. That is why I'm late. So, indeed, hopefully I'm recovering. Hopefully I am recovering. But thank you so much for asking. Thank you indeed. Fear, I like the username that you have. Hopefully we don't have to fear you, Fear. Sanju Pramanik says, are you Indian? Alfonso Carbajal says, hi. Hi, Alfonso. Thank you so much for the heart emojis. Could you double tap the screen and give us some likes on this live, please? And thank you. Can we get 20 likes? Alfonso says, hi. Fear says, you're one of the few people who possess a unique charm and likability that I've never, ever encountered before. I'm just being honest, bro. Thank you, bro. Thank you. Mexi Ghost Hunter says, how are you this night, my dearest friend? Thank you so much, Mexi Ghost. I'm good. I'm recovering from an upset stomach that led to some urgencies tonight. Maria says, hi. Hi, Maria. Maria, love the name, Maria, darling. Emma Roblox says, hi, you're beautiful. Emma Roblox, thank you, honey. Thank you so much. Fear says, thanks. Alfonso says, I did. Oh my gosh, well, Alfonso, you're just the best. Thank you so much for liking the live. Could you please, everybody, double tap the screen and please do like the live. And if you're here still, feel free to put anything in the chat. I'll read your messages. I'll read your comments. And I will give you a shout out. Thank you so much. Oh, thank you, Emma, darling. Thank you, Roblox. Emma Roblox says, I subscribe. Thank you so much. Please do like, share, subscribe. We need the help. We do need the help. Indeed, on this channel, we appreciate your help very, 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 very much. In fact, I am pooping my pants almost at this point, quite literally. We need the help. Well, and not right now. I was. Now in the present moment, I am here and I have fresh clothes on and I took a shower. So thank you so much. Maria Panduro says, yeah. Hello, Maria. Thank you, darling. Alfonso says thank you. Of course. Cornea Juan Juliantho. Cornea Juan says ciao. Ciao, sorry, what am I even saying? Ciao, Cornea Juan. Cornea Juan. I love it. Cornea Juan. Imagine all the people. I sometimes break into song. So if you're here, you may see some of that. Let me just say all your names again because I want to. Because I appreciate you all very, very much. Mexico's Hunter, thank you. My friend, thank you for being here. If you're still here, thank you so much. Fear, Sanju, Alfonso, Maria, Emma, Alfonso again, Cornea Juan, and Maria and Alfonso. Okay, got it. I think I got everybody. Thank you so much, everybody. Let me have some wawa, some agua. So we have been studying and talking about the origin and the fate of the universe utilizing the book called A Brief History of Time by Stephen Hawking. So that's sort of the discussion that we've been having recently. And we are almost done with this discussion, hopefully, because it's been going on for quite some time. This chapter in this book is quite long. And also we've been pondering a few things along the way. So hopefully maybe tonight and by tonight and tomorrow, because we go live on most nights, really. On most days, I would say some of the times it's in the afternoon, like a walking live. Sometimes, a lot of the time, it's a nighttime like this right now. But, you know, this origin and fate of the universe is quite a long and drawn topic. So hopefully we will wrap it up soon here. But we have learned some very interesting things, so we will see how this all goes. Mexico's Hunter says, has your cat ever acted creepy at night? My black cat is meowing under my bed oddly. Well, I hope your black kitty cat is okay. I mean, I think when they meow or they say something, it's really they're trying to get your attention. They just want to either play or get attention, get love, food, treats. But mainly, I think sometimes when they're well fed, and it's not really their meal time. So one of my kitty cats one of my kids who is a kitty cat is up to some trouble right here, right now. And pretty much when they're doing something out of the way like that, like getting up to some kind of trouble, pushing things off the counter, meowing, they're basically wanting your attention and your love. So black cat, white cat, whatever, they just want your love for sure, because they're little babies. My Shona Mono, my Shona Mono, Shona Mono Fuji. Mama loves you. Mama loves you. Fuji's looking right at me. Mama loves you, my baby. Mama loves you, baby. Fuji, Shona. So Fuji doesn't like to show his vulnerabilities too much. So if I pick him up and I give him too much love publicly, then he does not appreciate. He likes to be the man of this house and not show any vulnerability. He has an avoidant attachment style. He only lets mama love him in private under the blankets. So, or when nobody is watching, not even other cats. So, I'm looking at him because he's just a breathtaking view. I love my baby so very much. Thank you, universe. Thank you so much. Thank you for your help, support, protection, blessings, kindness, and guidance. Alfonso sent some emojis, hearts, and other things. Thank you, Alfonso. Can we do scary stories? Well, we can. Oh my gosh. Well, we might be reading about dark energy soon here, and that could be that may count as a scary story. I don't know if it really does. It's a mysterious thing that makes our universe expand, so maybe that counts as a scary story. But let me think. Do I have a scary story? I actually don't like horror. In the movies, when I go for the movies, if I accidentally watch something horror or scary, it actually is quite scary for me, and I don't like it, and I really don't like gory. I don't like gore, and I don't like horror. So, yeah, Mexico says, Mexi Ghost Hunter 86 says, Mama loves you, Fuji. Mama does love Fuji. Love you, baby. Love you, Baji. Oh, Baji's eyes are closing over here because Baji always relaxes with my voice in the background, and that's actually how this channel got started. It's the cats and my voice and all that. Alfonso says, Mexi Ghost is nice. Yes, most people on the channel are generally nice that join the lives, and some of them have even made friends with each other. And when they join, they start their own chatting and their own story time in the chat. But I think maybe some of them are already in bed at this time. So sorry about that. Sorry about missing people here tonight because of my bit of a stomach upset stomach situation. I missed going live earlier. I was still in the bathroom, and then I showered, and then I'm here. But Mexi Ghost from California and everybody else who is maybe in a different time zone is all right because it's late here, meaning it is not so late, hopefully, if you're behind our time. 1, 2, 3, 4 on the clock. It is 12:34, so not too late, but I could see it being kind of late for the weeknight for some of the people who have to work tomorrow Eastern time zone. So yeah. Anyway, here we are. If you're seeing this later on as a video upload, thank you so much. No worries about missing it because we were late. Don't worry about it. Just watch the video, listen to it in the background, and catch up with us and put anything you would like in the comments, and I will read all your comments tomorrow. So as soon as this video does go live and get uploaded under the live tab, do give us your feedback and comments and such. Mexico says, my cat Oprah is possessed. Really? Oh my gosh, with whom? With what? With which spirit is she possessed? Oprah, the possessed kitty cat. With which spirit indeed are we possessed? Lalo Salamanca, thank you for that emoji. Thank you so much. Meti Grandong says, hey beautiful, I'm love spit you with you. Thank you, Meti. Thank you indeed. Appreciate your comments. Jonathan said, hi Jonathan. Jonathan C says, if we have fingertips, but not toe tips, why can we tiptoe but not tip finger? Love it. Kramos, I love that username. Cramos, Kramos says, Baji the handsome cat, hello, greetings from Chile. Chile, welcome. So glad to have you here. Welcome to the channel. Welcome to the live, Chile. Love it. Matty says, I'm love, drink, spit you. Okay. The love and the drink and the spit are, I suppose, all good. Thank you so much for being here. And, oh, are you doing the tu as in evil eye remove? Then I really appreciate it. I should do the evil eye remove as well. Thank you, universe. Thank you so much for all your help, support, protection, blessings, kindness, and guidance, especially during challenging times towards myself and my children, my babies, Fuji, Suji, Baji. Thank you, God. So, but oh, I forgot to do all the continents. Hello and welcome to Asia, Europe, Africa, South America, North America, Australia, Antarctica, and Australia and New Zealand, of course, as well. Because, you know, I think Australia, kind of that continent means also New Zealand. But I like to call out New Zealand separately because I have a soft spot in my heart for New Zealand. I've had some very special interactions with people from New Zealand pertaining to my previous work. So all of that. And yes, so thank you, New Zealand, and hopefully I got all the rest of the continents as well. Thank you, South America. Thank you, Chile, for being here. Did you know that in one of my videos in the cemetery, you can hear a ghost voice? Oh my gosh, do you believe in ghosts? Oh, let me share the live. Oh my goodness. Do you really have ghosts in your videos, Mexi Ghost? Oh my gosh. Gosh, oh gosh. That's quite a development. That's quite the news for me. um 1 second, my friend was messaging me. I will get out of that. I will turn down the volume and I will go to my channel and then I will share the live. Did you know that in one of my videos in the cemetery you can hear a ghost voice? Oh no, wow. Yeah, it's in one of my oldest vids. Oh my gosh, I'll have to check it out. Thank you so much for sharing. Okay. Okay. But in the beginning, you can hear a girl whisper something. In the beginning, you can hear a girl whisper something? Oh my gosh! Well, that's quite scary. All right, let me put on the channel that we are live. We are live. Oh, I think Doro said that he's going to be traveling, so perhaps he cannot join tonight anyways because he's traveling. In the beginning, you can hear a girl whisper, best to hear it with earphones. Oh gosh. Okay. All right. So let's keep going with a little bit of this reading from the book, A Brief History of Time by Stephen Hawking. While my stomach allows me, let me do a little bit more of the reading and get ahead here. Steven Spears says, hey, Audrey. Hi, friends. Hello, my friend. Hello. So as far as my stomach will permit me, let me keep going with the reading a little bit and discuss some more of the origin of the universe from this book, Brief History of Time, Stephen Hawking. The Bears. Hello, Stephen. Stephen says hello. Gary. Hello, Gary. Oh my gosh. Wow. Gary. I haven't seen you in forever. Stephen Spears, my goodness, my friend, hello, how are you? The Bears said hello. Mexi Ghost said Stephen. And Gary says Baji, hello once again. We are here, Gary. We're here. Here's the shelves behind me. Let's go thumbs up, friends. Yes, please do double tap the screen and we can like the live. Thank you. Oh, thank you so much, guys. Thank you for liking the live. Thank you, thank you, thank you. Thank you for the hearts and emojis and sending the little hearts that I see floating up. Thank you so much. Love it. Thank you, Gary. Thank you, Mexi Ghost. Thank you, Stephen. Thank you, everybody. Thank you for liking the live. Oh my gosh. Oh, I love it. Oh, I love it. Okay. So we are talking about the universe and its origin and fate as described by Stephen Hawking's book, Brief History of Time. And we've been seeing how there's been some difficulty with the singularity that is the Big Bang, from which we, of course, start, and various models, inflationary model and this model and that model, which would basically lead to our current understanding of the universe and certain important questions that we have about the universe that we kind of covered a few lives ago, where certain things about the universe, let's just say, are very finely balanced. Basically, there are some numbers, including, for example, the charge of the electron, or the number of baryons, the ratios of various things, such as in the cosmic inventory, dark energy, dark matter, normal matter, or baryons, neutrinos, photons. All of these things are sort of cosmically finely balanced to give us the universe that we live in today. And we have certain questions, especially also about the expansion of the universe. And Fuji Baba, Shona, Fuji is wanting to get my attention. Fuji Mama's here, Shona. I know it's not a coincidence that I discover you now. It's a causality. I always love your positive attitude, and your intelligence knows no limits. Gary, thank you. Thank you, Gary. Mexico says, I'll be back. Gonna make some PB&J. Yes, please come back. Yes, thank you so much for being here. Welcome to the live. Thank you. And I hope that many of you will stay and participate and listen to the conversation, or say something in the chat as well. So we have some questions about the finely balanced nature of the universe, and also about how the expansion of the universe is also very unique. It could have been expanding in a way that basically leads to a recollapse. So if the universe did not expand fast enough, then we could have recollapsed. If the universe expanded too fast, then we'll never recollapse. And also certain other things would be difficult. For example, why does the cosmic microwave background temperature is quite isotropic and homogeneous no matter where you look in the universe and no matter what direction you look in? So, because that would imply that back in the day when the universe was more young, early days of the universe, and I really don't want to say days because it might even be moments, depending on which part of the universe evolution you're talking about, or it could be millions of years or even hundreds of thousands of years. For example, the CMB, we consider it to be around 300,000 years when the universe was 300,000 years old. So the cosmic microwave background is considered to be this primordial. I love this stream because I love astronomy. Thank you, of course. Thank you for being here, everybody. Stephen, Gary, everybody, love it. The cosmic microwave background temperature, or the cosmic microwave background photons, is considered to be a primordial sort of photon signature. But actually, the universe was around 300,000 years old at that point. So again, it depends. It's sort of relative what you mean by the timelines of things in the universe and its evolution. But earlier on, the universe was not as expanded because the expansion has been happening, and there may have been time for light to reach from one region to another, so much so that the photons in the cosmic microwave background have the same temperature, for example. But that too was a question that we've been kind of exploring in this chapter. So questions like that and discussions like that about the universe is what this chapter has been about, and we will continue with it and see what else we find here. But those types of things are really things that you can't really take for granted in the universe because, the CMB temperature being homogeneous, isotropic, sometimes we call it the smooth universe, but then of course, even the smooth universe actually has certain little irregularities or spots of overdensities, which has led to, of course, the stars and the galaxies in the universe. And exactly how those overdensities came to be, how we have those irregularities, again, is a question as well. And what kind of drives them is another whole topic that we will get into at some point. So these are all little things, or they're not really little, but they're details that are worth investigating because it actually makes our universe quite interesting and unique. And the more we can understand, the better, because these are not, they don't seem to be, such a coincidence, if you will. And especially certain things are sort of a cosmology question versus a God question. Like if God did certain things to get our universe started in a certain way, for example, if you believe in a God, which is totally fine, you can or cannot, up to you. I think that's a more spiritual question, a personal question, whether you believe in a God or not. But we do ask whether some higher being had chosen certain initial conditions for the universe, such as its critical density, energy, rate of expansion, blah blah blah, which leads to the universe being a certain way, or is it something kind of different and it's not as finely tuned in the beginning as one might think. So those are things that we do explore in cosmology, if you will. Cosmology kind of gets close to a spiritual understanding almost. Not really, because it's still an experimental science. It's still within physics. It's still just a science. And we try to do what we can with experiment and observation and theories and testing things out. But at the same time, these deeper questions may also come up. No Dora tonight. No, not yet. I mean, he's probably in bed by now. I mean, or he said he's going to be traveling, so who knows? We don't yet have a complete and consistent theory that combines quantum mechanics and gravity. So this is the other thing, guys, is that we don't have a lot of agreement between quantum mechanics and gravitation. In other words, quantum mechanics and really general theory of relativity, because as you know, general theory of relativity is the updated theory for gravitation at this time. It's been the updated theory for gravitation for the last over 100 years. When Einstein worked on it back in the 1900s, 1915, 1916, 1917, those types of years were very pivotal, very important for relearning and sort of unlearning as well as relearning what gravitation really means on the scale of this universe, and even sort of in astronomy as well, if you will. So, but in the same century, like in the same 20th century, we also saw developments in quantum mechanics, and these two fields sort of developed a little bit parallelly, quantum mechanics as well as general theory of relativity, and also general theory of relativity, consequent other work, like, other understandings of cosmology, the universe, etc. And quantum mechanics and general theory of relativity not really having a lot of overlap can be an issue because both theories are a little bit wrong sometimes. So we will see what is in store for us here. We've kind of explored this quite a bit in the past as well from the other book that we also cover here, which is The Elegant Universe by Brian Greene. So let's see what Stephen Hawking says here. So we're fairly certain of some features that such a unified theory should have. So even though quantum mechanics and gravity don't have a lot of overlap right now, or don't really agree at this time, but if you were to have a unified theory, what types of features would you want in that unified theory? You would hope that it kind of covers and explains certain things that we want explained. It's almost like we want to place an order for a unified theory for whoever is bold enough to work on it. And then we want to see certain results come out of that. We don't want to just have a unified theory that claims to be one without giving us the results we want. It's almost like we have certain experimental results, certain outcomes, certain things that are known already. It's just that those two theories, general theory of relativity and quantum mechanics, can't independently explain everything. And there are points at which they don't really agree, and they don't really shake hands very well. So we want a unified theory to first of all explain these theories like GR and quantum mechanics to just fall out of this bigger theory, of the unified theory. And we want it's almost like placing an order for like this delicious mac and cheese or something, and we want to see the cheese in it, we want to see the bacon, we want it cooked a certain way, we know what it should taste like, it's just please now make the dish, so it's like we know what it should look like and taste like and what's certain results that should be part of the outcome of this, but it's just too difficult to make it. So somebody please do it. But we kind of know what we want from it, that type of thing, okay? So we're fairly certain of some features that such a unified theory should have. One is that it should incorporate Feynman's proposal to formulate quantum theory in terms of a sum of over histories. So Feynman also, Richard Feynman gave us nice contributions to particle physics, for example. So certain things about the particles interacting or annihilating with each other, making more particles, making other particles, going through certain interactions and certain, histories, if you will, over time, types of things. Basically, it's a detail. So what that sentence really means is it's a detail of particle physics. Those details of particle physics, those details of quantum mechanics need to be part of the unified theory. If the unified theory cannot give us quantum mechanics and particle physics because we have overwhelming evidence for both, for experimental outcomes and evidences and results that have, discovered new particles, discovered new types of interactions. If the unified theory cannot give us that, then it's a dud. Then we don't like it. Because it's almost like saying, hey, listen, we understand that particle physics and quantum mechanics are inconvenient and kind of mysterious and kind of bizarre, but it's the reality. They have certain experimental results and outcomes and observations, such as particles and muons, existing sometimes and then decaying, and those are just a fact of life. So even though particle physics and quantum mechanics is not always the most elegant of theories, it's not the most elegant of realities, it is the truth that we have to accept and we have to explain with the unified theory if we are to claim to have one. Okay? So one is that it should incorporate Feynman's proposal to formulate quantum theory in terms of a sum over histories. In this approach, a particle does not just have a single history as it would in a classical theory. Instead, it is supposed to follow every possible path in space-time, and with each of these histories there are associated a couple of numbers, one representing the size of a wave and the other representing its position in the cycle, its phase. So its position in this cycle, its phase. So we can talk about waves and phases and all that later on, but if you understand waves, then this is pretty easy. The probability that the particle, say, passes through some particular point is found by adding up the waves associated with every possible history that passes through that point. When one actually tries to perform these sums, however, one runs into severe technical problems. The only way around these is the following peculiar prescription. Peculiar prescription. One must add up the waves for particle histories that are not in the real time that you and I experience, but take place in what is called imaginary time. Imaginary time may sound like science fiction. So complex numbers have a real and an imaginary part to them. If you're familiar with math and complex numbers, then this should not be too shocking. There is the real part, and then there is the imaginary part of any number, actually, right? And we call them complex numbers in mathematics. So that's what Stephen Hawking is kind of talking about here, is that imaginary time. So because there could be an imaginary part of this. Imaginary time may sound like science fiction, but it is in fact a well-defined mathematical concept. If we take any ordinary or real number and multiply it by itself, the result is a positive number. For example, 2 times 2 is 4. But so is minus 2 times minus 2. There are, however, special numbers called imaginary numbers that give negative numbers when multiplied by themselves. The one called I, when multiplied by itself, actually gives minus 1. 2i multiplied by itself gives minus 4, and so on. So he's talking about complex numbers math. This is something that we learn in math. And if you took this type of imaginary numbers math, then you know this already. But basically, he just introduced the imaginary number I. One can picture real and imaginary numbers in the following way. The real numbers can be, so again, sometimes we say complex numbers because complex numbers are basically numbers that have a real part and an imaginary part. And sometimes we just call them imaginary numbers, but we assume that there is a real part as well. Hi, Safia. Hello, Safia. How are you doing? Kaise ho aap? So one can picture real and imaginary numbers in the following way. The real numbers can be represented by a line going from left to right with 0 in the middle. Negative numbers like -1, -2 are on the left, +1, +2 are on the right. Then imaginary numbers are represented by a line going up and down the page. So it's vertical. It's perpendicular to this real number line, with I, 2i, etc. above the middle, and -I, -2i, etc. below the middle. Thus, imaginary numbers are in a sense numbers at right angles to ordinary real numbers. So this is exactly how we do it in mathematics. In complex numbers will sort of be somewhere on the page of this two-dimensional page that we just described, where this way, the left-right way is the real part, and the top-bottom way is the imaginary part. And basically, complex numbers are a mixture of having a real part and an imaginary part. And depending on where they lie on the page, you figure that out. So, to avoid the technical difficulties with Feynman's sum over histories, one must use imaginary time. So the thing is, with understanding this particle physics stuff from Feynman, you have to deal with imaginary time, and good thing that we have such a way already in mathematics. So it's all good. That is to say, for the purposes of the calculation, one must measure time using imaginary numbers rather than real ones. This has an interesting effect on space-time. The distinction between time and space disappears completely. A space-time in which events have imaginary values of the time coordinate is said to be Euclidean, after the ancient Greek Euclid. So Euclid in mathematics is named after the Greek guy Euclid, and who founded the study of the geometry of two-dimensional surfaces. So when we do geometry and mathematics in two dimensions, basically stuff that you can do on a piece of paper, that is called Euclidean geometry. What we now call Euclidean space-time is very similar, except that it has 4 dimensions instead of 2. In Euclidean space-time, there's no difference between the time direction and directions in space. On the other hand, in real space-time, in which events are labeled by ordinary real values of the time coordinate, it is easy to tell the difference. The time direction at all points lies within the light cone, and space directions lie outside. In any case, as far as everyday quantum mechanics is concerned, we may regard our use of imaginary time and Euclidean spacetime as merely a mathematical device or trick to calculate answers about real spacetime. So it may be something that is just a mathematics of this. It doesn't have to be also something in real life, but it helps us to do and formalize the math for all this, okay? A second feature that we believe must be so this type of feature of needing to do the imaginary time and to get the Feynman stuff to work out for particle physics, basically all of that was to say there's some details of particle physics that need to come out of the unified field theory, because it's something that already exists in particle physics, which has experiments and outcomes already, so we better be able to contain that in the unified field theory. A second feature that we believe must be part of any ultimate theory in Einstein's idea that the gravitational field is represented by curved space-time. Particles try to follow the nearest thing to a straight path in a curved space, but because space-time is not flat, their paths appear to be bent as if by a gravitational field. So let me read that again. This is actually quite interesting. So a second feature that we believe must be part of any ultimate theory is Einstein's idea that the gravitational field is represented by curved space-time. So actually, that's true. The mathematics that Einstein does for his general theory of relativity is not the usual type of math. If you actually see a long time ago, we had some lives on this math where we define like the geodesic, the metric, all this stuff. It's actually curved, this whole like curved space-time thing. There is a mathematics which is kind of different than our usual mathematics that is used for that. So let's see what he says. Particles try to follow the nearest thing to a straight path in a curved space. So basically he uses this 4 space-time as the mathematics, right? He uses time and the 3 spatial coordinates, and really the 4 space-time in Einstein's work is basically your new geometry. So it's not it's not the typical Euclidean geometry. You have to define out what things, how the math will flow in that particular geometry. And we spent some time on this on a live earlier. A while ago, I think it was called Einstein's equations, but we basically had to define things like metric, geodesic, all these types of things. The sort of this way of defining for space-time and how what a straight line means in a curved space-time kind of mathematics is a little different, right? So that's the sort of thing that you need in that particular math. So a second feature that we believe, Mexi Ghost, hello, thank you for being here. Enjoy your snack. Thank you so much. A second feature that we believe must be part of any ultimate theory is Einstein's idea that the gravitational field is represented by curved spacetime. Oh, another thing, remember, very interesting about GR, which is the general theory of relativity, is that gravitation is not a force in GR. It is the curvature. It's the bending of space-time. So we actually take the second derivative of position in that particular math, and we equate that to 0. So it's almost like saying the force is equal to 0. You know what I mean? Because gravitational force is not a force really in GR. It is the fabric of space-time, the bending of space-time. So it's very, very interesting, actually. Very, very, very interesting. Where's your coffee? Oh my gosh. Well, it's too late for the coffee right now, but thank you so much. I'll have to have it in the morning. Actually, maybe I should do one of my lives with my coffee in the morning so that you can see my coffee drinking. And thank you so much for your coffee money. Thank you. It's but that's funny. I have my water with me, but it's too late for the coffee. I want to go to bed at some point too. So, but thank you. Thank you everybody for all your support, help, everything, super chats and everything. Thank you so much. So, a second feature that we believe must be part of any ultimate theory. So any ultimate theory as in the unified theory. Did you get my PayPal? Oh, I'm gonna check after I read this part. I did you just send it? I'll check it. I'll check it soon then. I don't think I saw the email for it yet, but I will check. I will check while I'm live. A second feature that we believe must be part of any ultimate theory is Einstein's idea that the gravitational field is represented by curved space-time. Particles try to follow the nearest thing to a straight path in a curved space. But because space-time is not flat, their paths appear to be bent. So basically, space-time is not... did you get my PayPal? Let me check my email right now. Thank you so much, Maxi Ghost. Thank you so much for your support. Let me confirm with you. About that. Let's see. I'll go to my spam folder. I don't see it. I don't see it yet. Did you just do it? If you just did it, then maybe PayPal hasn't emailed me yet. But usually when I get something on PayPal, I get an email. That's why I was checking my email. So sorry, I didn't get it. I don't see the email yet. Thank you though. Thank you so much. Maybe PayPal will email me in the morning. I don't know. I don't know what they do. Usually when sometimes sends me something on PayPal, I'll get it as an email, but usually I see it in the morning because like that's when I'm checking my email. But maybe they only send, or actually no, I don't think that's true, because sometimes you know how I fill out those opinion reward surveys that pay you, and usually I think that I get the email right away. I hope that your money went to the right spot. It's the PayPal link on in my bio for Baji the handsome cat. So Hopefully it's not lost somewhere. I would hate for anybody to take a money loss here. Don't lose money. Okay. So actually, isn't it Warren Buffett who says there are two rules about money? Number one, don't lose your money. Number two, don't lose your money. So anyway, in the Einstein mathematics for general theory of relativity, his sort of flat is curved, basically. So he's using the four space-time, one time coordinate, three spatial coordinates. And that particular mathematics is curved space-time. Space-time is not flat, it's curved. And so a straight line is kind of bent, if you will. And so when a particle goes to its nearest, if a particle goes to its nearest point, it's actually following a curved path because the flat is the curved in the curved space-time. So once again, a second feature that we must believe, that we believe must be part of any ultimate theory is Einstein's idea that the gravitational field is represented by curved space-time. Particles try to follow the nearest thing to a straight path in a curved space, but because space-time is not flat, their paths appear to be bent as if by a gravitational field. So even though gravitation is not a force, so actually we set the second derivative of position to 0 actually, if you follow that math, but it's following a straight line in a curved paradigm. So the shortest path, all that is technically curved. If I die in this timeline, where do I go? Hello, useless, toothless, hopeless, lovely username. Is there a best way to die from a scientific standpoint? Oh my gosh, well, let me give that a thought while I keep reading for a while here. Let me finish this paragraph. But toothless, why so sad? Don't be with us. Listen to the science topic. So, particles try to follow the nearest thing to a straight path in a curved space, but because space-time is not flat, their paths appear to be bent, as if by a gravitational field. When we apply Feynman's sum over histories to Einstein's view of gravity, the analog of the history of a particle is now a complete curved space-time that represents the history of the whole universe. To avoid the technical difficulties in actually performing the sum over histories, these curved spacetimes must be taken to be Euclidean. That is, time is imaginary and is indistinguishable from directions in space. To calculate the probability of finding a real spacetime with some certain property, such as looking the same at every point and in every direction, one adds up the waves associated with all the histories that have that property. Thank you for being in the live. Thank you so much for liking the live. Can we get 20 likes? In the classical theory of general relativity, there are many different possible curved spacetimes, each corresponding to a different initial state of the universe. So this is another thing, is that you can have different initial states of the universe. You can give it a go and see what that looks like, right? If we knew the initial state of our universe, we would know its entire history. So that's another very cool. Similarly, in the quantum theory of gravity, there are many different possible quantum states for the universe. So quantum theory of gravity, if you were to have one, you could give it many different states and be like, okay, well, these are all the different possibilities for this universe. Again, if we knew how the Euclidean curved spacetimes in the sum over histories behaved at early times, we would know the quantum state of the universe. So because these are the sort of the sum over histories, whatever happened back then, if we can somehow get this, then we would know pretty much the quantum state of the universe. In the classical theory of gravity, which is based on real space-time, so this was the quantum way of thinking of it. Now, classical theory of gravity, like the general theory of relativity, is not a quantum theory. It's a classical theory, if you will, which it does not incorporate quantum mechanics into the theory, in other words. So it's based on real space-time, no imaginary, no sum over histories, no Feynman, okay? So, which is based on real space-time, classical theory of gravity, there are only two possible ways the universe can behave. Either it has existed for an infinite time, or else it had a beginning at a singularity at some finite time in the past. So, either it has existed for an infinite time, or else it had a beginning at a singularity at some finite time in the past. And remember, we don't really like singularities. Singularity is a mathematical sort of object where basically the physics is breaking down. It's sort of this point of infinite density. Another type of singularity that we've spoken quite a bit about, and the other main type of singularity in physics, is of course black holes. Black holes are also singularities. So singularity is a thing in nature. It's not like that it cannot happen. It's just that Big Bang is a type of singularity, black hole is another type of singularity. So once again, either it has existed for an infinite time according to general theory of relativity, or it had a beginning. We think it had a beginning. Big Bang theory thinks that it had a beginning, and that beginning is from a singularity at some finite time in the past. We think, according to the Big Bang theory, there is even a show named after this. We think it's around 14 billion years old. That's when the singularity, that's where the universe started from, that singularity. In the quantum theory of gravity, on the other hand, a third possibility arises. Because one is using Euclidean spacetimes in which the time direction is on the same footing as directions in space, it is possible for spacetime to be finite in extent and yet to have no singularities that formed a boundary or edge. Spacetime would be like the surface of the Earth, only with two more dimensions. So just like the Earth is a curved surface, you know, space-time is kind of like that, but with two more dimensions. There are three spatial dimensions and one time dimension, whereas Earth is a little bit different. Earth has two dimensions, and it's curved. So if you are a curved thing with two dimensions, then that's Earth, the surface of the Earth. If you are a curved thing with four dimensions, then you are a curved space-time, like in GR. So anyway, or well, space-time would be like, because of the quantum gravity thing, space-time would be like the surface of the Earth, only with two more dimensions. The surface of the Earth is finite in extent, but it doesn't have a boundary or edge. If you sail off into the sunset, you don't fall off the edge or run into a singularity. Luckily for the sailors and people who are on boats, if you sail off into the sunset, you can just continue to sail, or you will hit land at some point, but you don't run into a singularity, thank goodness. Not yet, anyways, not that we know of. I know because I've been around the world. Stephen Hawking says. Stephen Hawking has gone around the world, and so he knows that you can indeed go around, all the way around. Thank you, Toothless. How are you? If Euclidean space-time stretches back to infinite imaginary time, so because in quantum, in the Feynman sum over history's way, in the quantum way, we allow for infinite imaginary time, right? We allow for infinite imaginary time. So if Euclidean space-time stretches back to infinite imaginary time, thank you for liking the live. Thank you so much. Can we get 20 likes? And thank you for the hearts. If Euclidean space-time stretches back to infinite imaginary time, or else starts at a singularity in imaginary time, we have the same problem as in the classical theory of specifying the initial state of the universe. God may know how the universe began, but we cannot give any particular reason for thinking it began one way rather than another. On the other hand, the quantum theory of gravity has opened up a new possibility in which there would be no boundary to space-time, and so there would be no need to specify the behavior at the boundary. There would be no singularities at which the laws of science broke down, and no edge of space-time at which one would have to appeal to God or some new law to set the boundary conditions for space-time. One could say the boundary condition of the universe is that it has no boundary. How to PhD? Yes, Mexi Ghost Hunter. Did you find my blog? So the boundary condition of the universe is that it has no boundary. Aw. Oh my goodness. Well, Toothless has asked a very important question. Why do you not just give up? Let me come back to that question in just a little bit, okay? Thank you so much for being here and thank you for asking that. The boundary condition of the universe is that it has no boundary. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. I kind of resonate with that actually. I like to just be. I don't like to be created or destroyed. Not any more than I already have. I just like to be. I like to be. I like being with the universe. Let's continue to be. Oh, thank you. Did you send again? Oh, or you tried to? Thank you so much. It was at the conference in the Vatican mentioned earlier that I first put forward the suggestion that maybe time and space together formed a surface that was finite in size but did not have any boundary or edge. My paper was rather mathematical, however, so its implications for the role of God in the creation of the universe were not generally recognized at the time, just as well for me. At the time of the Vatican Conference, I did not know how to use the no boundary idea to make predictions about the universe. So Stephen Hawking had gone to this conference in the Vatican. However, I spent the following summer at the University of California, Santa Barbara. There, a friend and colleague of mine, Jim Hartle, worked out with me what conditions the universe must satisfy if space-time had no boundary. When I returned to Cambridge, I continued this work with two of my research students, Julian Luttrell and Jonathan Halliwell. Not everybody creates children, the new ones anyways. But some people do, some people don't. Thank you for that question as well. So I'd like to emphasize that this idea that time and space should be finite without boundaries. So this is sort of, looks like it's going to be sort of a work in progress here, because it's quite, it's pretty difficult stuff. I'd like to emphasize that this idea that time and space should be finite without boundary is just a proposal. It cannot be deduced from some other principle, right? It's not something that he's deducing from some other principle. My hair is very wet still, so I'm just fanning it out a little bit. Like any other scientific theory, it may initially be put forward for aesthetic or metaphysical reasons. But the real test is whether it makes predictions that agree with observation. So that's the real test of anything in physics really, is does it make predictions and agree with observations? Physics is an experimental science. So if you want to make a theory, make a prediction, great, but you have to kind of make it agree with experimental outcomes or experimental observations. You have to make sure that it agrees with that. If not, it's just a theory. This, however, is difficult to determine in the case of quantum gravity. For two reasons. First, as will be explained in chapter 11, so we'll get to that, we're not yet sure exactly which theory successfully combines general relativity and quantum mechanics, though we know quite a lot about the form such a theory must have. Second, any model that described the whole universe in detail would be much too complicated mathematically for us to be able to calculate exact predictions. One therefore has to make simplifying assumptions and approximations, and even then, the problem of extracting predictions remains a formidable one. Each history in the sum over histories will describe not only the space-time but everything in it as well, including any complicated organisms like human beings who can observe the history of the universe. So this might be related to what you were asking a moment ago. Useless, toothless, because pretty much human beings do care about this stuff. It gives us some purpose. Some of us do like to understand how this universe got started, and understanding cosmology is important to us. It gives us a certain sense of purpose. It's sort of that the reason for all of this is because we're curious. It's the inquisitiveness and exploratory nature of the mind that makes it imperative that we sometimes study these types of things. And a lot of people care about understanding these things. So now, it is true that if you don't care, then that's also fine. The universe will exist nonetheless, for sure. And the concept of time that you were asking about too, in this context, it's sort of part of this four space-time mathematics. So that's really the definition of, that's really the context of it. In general, if you don't measure the time and you don't care about it, then that's totally a fine way to live as well. Fine way to live as well. So, and in fact, time is relative. So, indeed, the measurement of time as far as how much time has passed, that is relative depending on what you're, depending on your frame of reference, and depending on which which massive body you're close to, because a massive object will bend space and time. So measurement of time as far as how much time has passed, that question that you asked, that's the context of time in that sense. Time dilation, relativity making time different depending on your reference frame. But this time that we're talking about in the sense of space-time, geodesic, metric, general theory of relativity, quantum gravity, the dimensions that you need to set up the math for all this, that time is which is a little bit different as we find here in relativity versus quantum gravity, because in quantum we allow the imaginary time in the math as well. So that time is not so much about measuring clock time. It is, time is given the status of a dimension in the geometry. Okay, so all right, so then any model that described the whole universe in detail would be much too complicated mathematically for us to be able to calculate exact predictions. One therefore has to make simplifying assumptions and approximations, and even then, the problem of extracting predictions remains a formidable one. Each history in the sum over histories will describe not only the space-time but everything in it as well, including any complicated organisms like human beings who can observe the history of the universe. This may provide another justification for the anthropic principle, for if all the histories are possible, then so long as we exist in one of the histories, we may use the anthropic principle to explain why the universe is found to be the way it is. Exactly what meaning can be attached to the other histories in which we do not exist is not clear. This view of a quantum theory of gravity would be much more satisfactory. However, if one could show that using the sum over histories, our universe is not just one of the possible histories, but one of the most probable ones, To do this, we must perform the sum over histories for all possible Euclidean spacetimes that have no boundary. Using or under the no boundary proposal, one learns that the chance of the universe being found to be following most of the possible histories is negligible, but there is a particular family of histories that are much more probable than the others. These histories may be pictured as being like the surface of the Earth, with the distance from the North Pole representing imaginary time, and the size of a circle of constant distance from the North Pole representing the spatial size of the universe. Hello. Hi, how are you doing? Kauba Luke Ben says, hello, lovely girl. Thank you. How are you? Hello, Kauba. The universe starts at the North Pole as a single point. As one moves south, the circles of latitude at constant distance from the North Pole get bigger. So this is the North Pole and South Pole of the universe. I know. This is getting a little complicated, isn't it? Jose is saying, what is gravity? Does it change time? Yes. So gravitation is a bending of space-time. And if you have a very massive object, it will bend space-time more. So gravitation, according to general theory of relativity, gravitation is a bending of space-time by massive objects. And so the more massive an object is, the more it will bend space-time around it. And so it can change the experience of time around that particular body. And as in, time will be relative. Time is relative, absolutely. Time is relative in special theory of relativity as well. But special theory of relativity is basically saying space-time is relative, but it's a specific case of relativity where it works for only inertial frames of reference. So you have to be either at rest or a constant velocity for special theory of relativity to work. General theory of relativity is more general. So you can be accelerating, you can have gravitation, because remember, special theory of relativity does not actually concern gravity. Gravitation makes us accelerate, and there's no acceleration allowed in special theory of relativity. It's for inertial frames only. So, but as for the question about is time relative, yes, and indeed, gravitation can change time. You can have relative time because of gravitation. Yes. So that was Jose who asked that. Gurveer says that just went over my head. That's okay. We are sort of covering a more difficult topic right now, so bear with me. Maybe we'll illuminate it further in just a second here. Hopefully we will get into more illumination of what's happening. Bicycle Gaming, hello. Hi, Bicycle Gaming. I'm not founder live and not looked. Well, are you subscribed to my channel and do you get notifications? And also I share the live on my channel when I go live, so hopefully you see it. Sometimes people are not notified when I go live for whatever reason. It's a bug on YouTube. Kauba Luke Bin, thank you so much for the shiny hearts. Really appreciate all the hearts and the shiny. Oh, let me check my email again. I think Maxi Ghost sent me something. Yes, are you coming? Who is this? Oh, my friend is texting me. Oh my gosh, Maxi Ghost! Thank you so much for the PayPal. I think this is from you. You said you sent me and I just got it. Payment received. Oh my gosh, thank you so much. Oh my gosh. Tell us your name. It's me, Maxi. Mexico sent me $60. Oh my goodness. Oh my goodness gracious. Oh yeah, absolutely, absolutely. Thank you so much for sponsoring the live, Mexi Ghost Hunter. Mexi Ghost Hunter 86 says, "Good night, my dear friend. Nice being here with you. I wake up early for work tomorrow, 5 a.m." Yes, absolutely. I get it. Thank you so much for the PayPal. Thank you so much for the Baji the Handsome Cat donation at the link in bio on my PayPal. Thank you so much. I really appreciate your kindness. Mexi Ghost just rocks. He's been supporting this channel, and thank you so much for your sponsorship. Bikel Gaming says, "I am subscribe your channel. I'm not getting." Yes, so I don't know, but sometimes I go live and it does not send people notifications. So please make sure you're subscribed and have the bell icon pressed or whatever. And I try to share the live as well on my posts on the YouTube channel. So hopefully all of that can notify you. And thank you so much for being here, everybody. Thank you. Mexicos, thank you once again for sponsoring the live and your very generous donation. Indeed, thank you so much. Very, very kind of you. And everybody else as well, thank you so much for being here. Kauba, Luke, Jose, Gurvir, Bikel Gaming. Thank you so much. Wow. Wow, guys. Love it. So I'll keep going for a little bit. Although this part is a little difficult. Actually, I'm going to show you the diagram on the book here really soon as well. So that will also eliminate some of the confusion, hopefully, or not eliminate, alleviate some of the confusion, hopefully. So we will see about that. Mexico says, "See you next time. Have a wonderful night." Thank you. Good night, Mexi. Good night. Good night, California. Good night, the United States of America, the people who are going to bed. Good morning, Asia. Good morning, Europe. Good morning, afternoon, evening, the rest of the continents, Africa, South America, Australia, New Zealand, Antarctica. I couldn't do all of the math in my head. I think Australia might be like afternoon right now. But thank you, Mexi Ghost. Good night. I'm also one YouTuber. Oh, very nice. Okay, so I'll show you the pictures here in a bit, but the history of the universe in real time, however, would look very different. At about 10 or 20,000 million years ago, it would have a minimum size, which was equal to the maximum radius of the history in imaginary time. At later real times, the universe would expand like the chaotic inflationary model proposed by Linde, but one would not now have to assume that the universe was created somehow in the right sort of state. So the universe would expand to a very large size, and eventually it would collapse again into what looks like a singularity in real time. You are my imagination. You are my fire. Reminds me of that song. The one desire. Believe when I say I want it that way. So when you wrote "You Are My Imagination," thank you. It reminded me of this song. Thank you so much. You are my fire. The one desire. If the universe really is in such a quantum state, there would be no singularities in the history of the universe in imaginary time. It might seem, therefore, that my more recent work, so Stephen Hawking's more recent work, had completely undone the results of my earlier work on singularities, but as indicated above, The real importance of the singularity theorems was that they showed that the gravitational field must become so strong that quantum gravitational effects could not be ignored. This in turn led to the idea that the universe could be finite in imaginary time, but without boundaries or singularities. When one goes back to the real time in which we live, however, there will still appear to be singularities. The poor astronaut who falls into a black hole will still come to a sticky end. Thank you for the heart emoji. Only if he lived in imaginary time would he encounter no singularities. Okay, we will stop here and continue this next time. Page 144, Brief History of Time, Origin and Fate of the Universe. Thank you so much. Thank you for the heart emoji, Bikel Gaming. Thank you so much. Gautam Buddha, yes. Thank you to Gautam Buddha. Thank you, universe. Thank you so much, everybody. Thank you, universe, especially. Thank you, Gautam Buddha, for all your help, support, protection, blessings, kindness, and guidance, especially towards me and the children, and to help me to take care of us. Thank you so much, all you lovely people supporting this channel, supporting the lives, really means a lot. And Goddess and Shivji, Hanumanji, absolutely. Goddess Durga, Shivji, I was named after her, Durga. So I do follow you, Goddess Shivji and Hanumanji. Could you please like the live, everybody? If you're joining, if you're seeing this later on, thank you so much indeed. Please do like the live. Please do like, share, and subscribe. Really appreciate all your support. It means a lot, more than you know. And thank you so much. Have a great night, USA, and great night and great morning, afternoon, everything to Asia, Europe, Africa, South America, North America, Australia, New Zealand, Antarctica, the Arctic too. Please do good, do well, have a great day. Have a wonderful, amazing time. I'm in live, all are not live. Okay. 1, 2. Okay. So, after this chapter, we will do the arrow of time. That'll be very interesting as well. Time. Then we will do wormholes and time travel. Oh, that's right. On this channel, we talked about wormholes and time travel, and a lot of people were interested in that topic, and they asked about that topic, and we read about it from a couple different other sources, such as Michio Kaku's book, Einstein's Cosmos. But there's a whole chapter on wormholes and time travel in this book by Stephen Hawking. Brief History of Time. So chapter 10 is going to be wormholes and time travel. So that will be very fun. Ooh, listen to this poetry. There was a young lady of white who traveled much faster than light. She departed one day in a relative way and arrived on the previous night. And with that, ladies and gents, we will take your leave for tonight. Einstein Rosen Bridge. And we will say goodnight for tonight and see you next time. Actually, I will leave you with a little picture here. So let me do that. That's the North Pole, South Pole thing that we were talking about with the universe. And see, there's the Big Bang, increasing imaginary time, Big Crunch, universe, size of universe is decreasing with imaginary time, and all such things. I will leave with that. Actually, let me show you. Maybe there is another. No, actually, let's see if there's another better picture. But where is morning? Good morning, if it's morning for you. Okay. Let you look at that. And I can even zoom in a little bit here. You are my fire, the one desire. Believe when I say I want it that way. You are my fire, the one desire. Believe when I say I want it that way. Hi Sludge. Sludge said, Sludge PLS said, I haven't seen a book in 20 years. It is an Earth. No, actually, this is the universe. But, you know, some geometry with the universe. One comment and go. Stefan, how are you? Hello, Michael. Hello, Stefan. Hello, Sludge. Thank you for being here. Thank you for joining. We will be live again tomorrow. Oh, please do like and subscribe. You are my fire. Thank you. See you. gosh. Thank you for being here still. Alright, I have to go to bed. Oh, let me show you my children though. Look at this. Everybody ready for bed, guys? Ready for bed? Oh, everyone is waiting for Mama to clean up and do a couple more things, and then we're gonna go to bed. Just gotta do a couple checks, go through my list, change the water, and then we're gonna be ready for bed. Thank you everybody so very much. We appreciate you so much. Thank you so much for all your support. Thank you for being here. Thank you for joining. Thank you for all your chat messages, comments. Thank you for watching this as a video upload later on. Thank you for the super chats. Thank you for the donations on PayPal. The PayPal link is in the bio, and I'm so glad that people are using it, and very much grateful and thankful for your support. Until next time, thank you so much. See you very soon. Good night. Good night.